Okay, welcome back, everyone. We still have power outage numbers, and we're going to have a lecture on Monday, by which time hopefully everyone will have been able to get power back. And I think on Monday, I'll do a lot of the same things that I've done in these two lectures. But I do need to test run the material, and also I'll just ensure that I have enough time. We're going to do a first pass through it, and you probably do need to see a first pass. Do you have any questions from last time? Right. So the first thing that I'd like to talk about is this idea of global definitions in more detail. And these are global. And the idea is that this is our replacement for the previous assistance that Proust gave us with writing proofs. In the presence of dependent types, writing proof terms piece by piece, where you have context and you have dependence on those contexts, is very difficult because things that you write in the term may affect other parts of the term. And it's much trickier to implement, but as a compromise, will allow you to write terms that make sense globally. So this is our replacements for wholes, which are much trickier to implement in the presence of dependent types. And the idea was that previously, for example, what is one way to prove? We proved, let's say A implies B. How? Assume that A and B are meaningful and that it's actually possible to prove this implication. There are various ways to do it, but what was the canonical way of doing it?
I believe we use the lambda rule of abstraction.
Yes. Assuming A and proving B. The proof term was lambda, let's say little a, and then let's say little b, where this is now, well, let's write t to make it clear that it's not a variable. Then when type checking, a lambda, what rule did we apply? Let's say in the case of predicate logic.
We called it implication elimination.
Well, in propositional logic, implication elimination was for applications, right? That's how you use a function. But how do you form a function?
I mean, like the preceding conditions necessary to make a lambda?
Well, implication elimination was the rule that we used for synthesizing the type of an application, right? This
Yeah.
rule was implication elimination. The grammar construct that corresponds to implication elimination is applications, not lambdas.
I thought that was implication introduction.
Implication introduction introduces an implication, right? So if you want to prove an implication,
Okay.
then it lets you introduce an implication. So this is implication introduction. Here you're forming an implication. Here you're using an implication in the conclusion, right?
Yes. Yeah, I am. Sorry.
Now, so the answer could be implication introduction, but let's say we're working in the world of predicate logic and we're going to call it for all introduction. And when we apply this, let's look at what that version of the rule looks like for us now. So let's say we, in context gamma, have a lambda term. Let's call it lambda little x and then t. And let's say we are trying to type check this against for all x in t w. Then what do we do?
We use implication introduction.
Yes, well, for all introduction, but what's the premises? What do I write here?
Oh, in context gamma, x.
Oh, let's first check that t is well formed.
Oh yeah, t type checks.
Yep.
Type.
Then
in context gamma and x as type t.
Mm-hmm.
T type check w.
Yes. Well, not yes, w, exactly. And this is the for all introduction rule. So in other words, when we have a lambda, we type check it by adding x to our context. Now, x is just a variable, and you can think of x then as a promise of a proof of t, of big T. You're assuming that you have some proof of t. And computationally, if you're provided a proof of t, it'll eliminate the lambda by substituting. So adding things to our context with the application, with the for all introduction rule really looks like assuming something, having a promise laying around. Well, definitions are a stronger way to introduce meaning to names. When you make definitions, instead of just having X stand for some promise for a proof, X actually has a proof term corresponding to it. So here, when we added X to the context, it stood for a promised term yet to be delivered. Now, in definitions, this proof already exists. So I'll give you an example. Let's navigate to use, does everyone see Rocket?
Yes.
Okay, so there is a functionality, and this functionality is the function def. Now, you take def, you give it a name. Let's say that name is, for example, ID type. And then you give it a term. So what is the ID type in last lecture was the type of the polymorphic identity function. Does anyone remember what type that was?
A is a type,
Mm-hmm.
and A to A.
So it'll just accept the definition. It'll process the definition and it'll accept it. If I, for example, tried to make a definition that didn't make sense, such as this, it would actually throw, oh, it'll say that it's already defined. You're not allowed to redefine something else. Let's say it's ID type 2, and then you have this B inside of it. So that does not make sense on the ground of the fact that that's not actually a type. You can't synthesize. And it'll say, cannot infer the type of B in this context, where currently we're adding an underscore, which is a bug that needs to get fixed. So in general, if you try and define something, it'll attempt to synthesize the type of this expression, and it won't let you make the definition if that type can't be synthesized. So to see why the first definition was allowed, if we run type synthesis in the empty context on what happens when we parse this expression, then what will it give me? What is the type of this expression?
Lambda capital A, and
The type of that expression, that's a term of that expression, but what's the type of that expression? Lambdas never define types. Well, going back for a second to the blackboard, remember what the rule was if we try and look at an expression like for all x in t, w, and let's say we try and synthesize the type of this. What type is synthesized and under what premises? Do you remember?
Annotation.
This is, but okay. What grammar term is this? This is the grammar term for formation of a for all expression, right? This isn't an annotation. Well, for example, let's say I had an arrow instead. Let's say I had gamma, and I just had, let's say, T implies W. What does this synthesize to? And under what premises? What is the type of T implies W? Well, what can the type possibly be? Let's give an example. Let's suppose we have natural numbers. What is the type of not implies nots? What type does this have? Or what about nots? What type does not have?
It's a type.
Yes. What type does not implies not have?
Type.
Yes. So in general, T implies W should have type. Should have type what?
Type.
Under what premises?
T is a type.
Yes. And?
And W is a type.
Yes. Okay, now what about the for all rule? When you have a for all expression, then this should be a type provided what?
T is a type. And in context gamma, X has
Good.
type T, W type check to type.
Good. So any questions about those rules? In which case, going back here to Proust, if I try and synthesize this type, what should I get?
Type.
Yep. And now, if I look at the current implementation, I can also try and synthesize the type, not of this expression, but I've already made the definition, but of the symbol ID type. And that'll just give me type. So the name ID type is introduced into the language. It's sort of like it's already in the context. We know that the ID type has type because that's what happened at the level of the definition. But what's stronger than that is that ID type actually reduces to this expression. So for example, we're going to have a function called strong reduce. And this function performs computation. So if I just take ID type and I perform computation on it, what will that expand to? So if I expand the definition, what do I get? Well, I get the thing to which I defined it. It'll write it right now as an arrow. If I, for example, pretty prints this, then it'll actually write that arrow underscore as an arrow. Then it'll, well, that should have formed implication. This version, that's very odd. Okay, that's a bug that needs to get fixed. That should have printed as an implication, definitely. Anyway. So in other words, global definitions are things roughly things in the context, but not only do they say that there are some variables which have a promise of a term of a given type, but there's actually a specific term associated with them. And you can always synthesize their type. So you can imagine replacing the variable in the definition with an annotation where that type already exists. So as another example, let's actually give a definition of the polymorphic identity function. How do I define the polymorphic identity function? So what is a term of ID type? You were saying it before.
Oh, that's lambda capital A.
Mm-hmm.
Lambda little a and A.
Yep. So this term should have type ID type. Now, before accepting the definition, it'll actually try and synthesize the type of this, and that synthesis will succeed. Now, I have IDs. So for example, if I say type synthesis, in the empty context, although global definitions are sort of this addition to the context, if I just try and synthesize the type of ID, it'll give me ID type. It won't expand it. If I try and strong reduce that, it'll actually expand ID type to the full, its name in full. And then if I strong reduce, this means perform computation on this symbol. It'll expand it to the definition of what ID is, the lambda term. Lambda A, capital A, lambda A dot A. And then if I, for example, pretty print that, it'll format as expected. Oh, the problem is that pretty print, I need -expr. Here we are. There are no bugs. I just wrote it wrong. For example, if we look at strong reduce ID type. Now, then the thing is that if we look then at the polymorphic identity function, we can take something like ID and then apply it to a type. The type we'll apply it to is ID type. And then we'll take this, and this is a function of ID type to ID type. So for example, we can say type synth in the empty context ID type ID of ID type. And what will I get as the type here? Well, let's see. I didn't parse. I'll get ID type implies ID type. then this means that I can apply it to any term of ID type, such as ID. And then I could try and synthesize the type of that, and it'll be just ID type. Now, if I look at this expression, this really should look like the identity function. So let's see what happens when I strong reduce this. Then it'll actually just form the identity function. It'll give me the identity function, but it'll expand the term as well. So it'll be lambda A, this. So that's how definitions work. And that's also how computation works. Strong reduce is this function which performs computation in full. And I can describe a bit more of what it does later. And then global definitions are things which are looked up, and in computation, after you look up that name, it's actually replaced with the term. When type checking or type synthesizing, the name type synthesizes to its type. But if you have a name in a global definition, then you can always synthesize its type. That's a requisite for having made the global definition. And then not only is it just like a thing in the context, it's also a thing in the context of a term already associated with it. So in computation, where you can actually take that promise and replace it with the term that's already supplied. Now, I want to also discuss one way. So last time we suggested that computation happened in several places. So one example was, let's say, in the for all elimination rule. So let's say you have some application and you want to synthesize its type. What do you have to do?
Maybe like synthesize the type of F and A individually.
Good. Well, you'd synthesize the type of F, and
Yeah.
you'd hope that it's for all.
Yeah.
And then what do you do?
And then you type check the type to A.
Well, A to what?
Yes.
I didn't hear that.
Type.
But let's look at it. F might be, it's for all X and T W, right?
Yes.
So if it were, the special case of for all would be an implication if X doesn't occur in W. Then A should be something of type what?
Maybe for all X of T.
That's what F is. So imagine that we just had the special case. Let's imagine that F synthesized type T implies W. Then for the application F applied to A to be well formed, what would you have to know about A?
Well, you would have to know that A is type check 2 by T.
Yes. So here you want to put what?
Yeah, the analog for T is, well, just the for all statement, right?
Yes.
Yes.
But T. not type, right? Not a for all, just T. And then what's the conclusion? What type do we synthesize?
And then we synthesize, oh, whatever type W is.
But W might have X occurring in it. So what do you have to do?
Oh, you have to take the X and, well, set it to substitute with something else. Like
What's that something else?
I guess just say like Y, an arbitrary term.
But what is Y? Y doesn't exist here.
Yeah.
Well, think about it like this. Suppose we have the statement, suppose that F is a proof of for all knots, or for all n in knot, n equals n.
Yes.
And let's say that A is Z. So F of Z would have type what?
It would have type. Well, it would still be an at because Z's an at.
Yes. Well, so you get an equality type is an
Z equals.
type. So what would you write?
Oh, Z equals Z.
Yes. So what did you substitute in place of n?
I substituted A, which
Yes.
is
So
Z.
here it should be Wx replaced with
A.
Good. So this is the for all elimination rule. Now, let's look at this. In this rule, we had to have the type that we synthesized be a for all. And implications are considered special cases of for all. But what happens if, for example, F is a global definition, and then we just replace it with the name in the definition? That doesn't have the form of a for all, but we would also like to say that those are equivalents. So one other way to write this definition is that, let's suppose that, so this is the computational version of this definition. The computational version is that we try and synthesize the type of F, and we synthesize some type, let's say V. Then we take V and we try and see if it's equivalent to A for all statements. And then assuming that we're able to make it equivalent to a for all statement, then we try and check A against T. Now, how do we check that this statement has the form of a for all statement? Well, the idea is that we take V and we perform computation on it. And if V is ever equivalent to something of the form of a for all statement, then once the computation stops, it either is of that form or it's impossible to make it of that form. And now, how do we perform the computation? Well, there's actually two different notions of how we do it. In this version, we're going to use a weaker form of computation called weak reduction. And what weak reduction does is basically weak reduction looks up definitions and applies weak reduction recursively, looks up definitions, and computes and evaluates or reduces applications onto lambdas. Meaning when you have something like lambda xt applied to s. So it'll just do those. And it'll repeatedly do that to v until it gets to a point at which there are no more definitions to look up, or there isn't an application onto a lambda at the top level. It won't recursively look inside each of the subterms. And so to show you what that function looks like, here's the weak reduce function. If there's a symbol, if it's trying to reduce an expression that's just a symbol, then first off, things that are bound to the context take precedence over global definitions in case you redefine something that's a global definition. So if it's already bound in the context, then it overrules global definitions. Otherwise, you'd actually look it up in the global definitions. And then once you get something from it, assuming that the lookup succeeds, you take the results and you weak reduce it again. And otherwise it does nothing if it's just a symbol. And if there's an application, then you take the first factor and you weak reduce the first factor, but not the second factor. And if it's a lambda, then you substitute and you weak reduce. Otherwise it does nothing. So weak reduction only performs these types of things. Any questions about that? So weak reduction is a very basic form of computation where the only thing that it evaluates is applications on lambdas and looks up definitions. Now, if we actually look at the rule for, so this is the rule for all elimination. We can also look at the for all introduction rule. So typically, well, we have the rule written above. Here, the for all introduction rule. If your term is a lambda, then you're trying to type check it against the for all, and the variables match up. Then you check that t is well formed, you add x and t into context, and then you type check the body of the lambda. So here's a computational version of that rule. So in general, suppose that what you have is that some lambda, you're trying to type check it against v. V might not be an for all statement at the moment, and the variables might not match up. Then what do you do? Well, what did we do before? Well, what did we do before? If it was a for all statement. Can I please get some replies?
Well, the for all statement is just on the above the one on top, right? That
Yes.
the computation
So
on top.
explain what we did in that statement.
Yeah. So, yeah. So this is going to be the application, right? So, what are these lambdas?
There isn't an
Oh, yeah.
application.
Oh yeah. Okay. Sorry, just that we used v in place of for all xt implies w. So
Right.
I guess first we type checked t to an arbitrary type, I guess.
Yes.
Why is that an uppercase t? Wouldn't it be a term? So a lowercase t.
Well, it's a metavariate, so right now we
Oh, I
don't
meant like on. Oh, I meant on top line.
this right here. Well, this t is the same as this t.
Okay.
So we're quantifying x over all terms of t.
Yes.
And then this little t is this little t. So there's a little t and there's a capital T.
Okay, so the for all statement is going to be encoded in the V.
Right.
So,
So, but we don't know if it has that form. So in general, we can perform a weak reduction on it, right? But before performing computation on it, we'd also like to check that it's well formed. So how do I check that V is well formed?
like well formed in the sense that it matches one of our syntaxes.
Well, V is supposed to be a type, and it's possible to write meaningless types, right?
Yeah.
Like you can write a quantification over a lambda.
Yeah.
So for example, the following type is not a well-formed type. Because the t in here is not well-formed. Remember how a while ago we discussed the rules about when this for all statement was a well-formed type? So these two rules express well-forming of types.
Okay.
So if we'd like to check that V is well-formed, what do we do?
Well, I guess we need to check if the type of X is checked to a type.
Well, X is a variable.
Yeah, but we had like capital T type check to type, and it was like for all xt, right?
Oh, so T is actually something that should make sense as type W, not as type T. I suppose that that's a possibly a bad thing. Maybe I should have replaced T and W in their order. But T is actually something of type W in a context where X has type T. So T is not a term of T, confusingly.
Oh, you meant lowercase t. Yeah, I meant like in the bottom line of that for all implication, you had for all X capital
Yes.
T. I meant like, if capital T was type check to by type, then I guess it's like for all.
Yes, but there's no capital T, so we should type check V instead to type, right?
Yeah, that would establish that V is indeed the proper type first.
I don't hear you.
Yeah, that would establish that V is a proper type first, and yeah, that leads to like 3 branches, I guess.
Yes. And then if it's a proper type, what can we do with it? So we'd like to bring it to the form of a for all statement.
Yeah. So then I guess we can do what we did like above, like set equivalent to a weak reduction of for all X T to W.
And now that we've performed the weak reduction, what do we do?
And now that we performed it, we can do the last branch for application, which is
Abstraction.
yeah, abstraction. Sorry. Yeah, I forgot what that last branch was. Hold on, let me just review for a bit. Oh, okay. So yeah, you added to the context
Right.
that X of capital T yields a little t that is type checked to by W, because as we said, little t is actually W.
Yep. Good. Yes. So this is the computational version of for all introduction. Here, I make it explicit as to where the computations are actually performed. When we try and basically match against a certain type, then we perform these checks. If V type checks to type, then and if it's something that's of the form of a for all statement, we'd be roughly guaranteed that both T and W are well-formed types. So the computational rule is a bit stronger because it'll also check W is well-formed. But these are the rules as they're implemented in Proust. So this makes it more explicit as to where computation occurs. And then in the final rule, if you look up variables, before, what did we have? If we had context gamma and we had, let's say, X, then we could synthesize its type to what? Or no, rather, instead of doing, sorry, I don't want the variable lookup rule. I want the term rule. Suppose I try and type check T to T. Then what does the term rule say?
That the context gamma also yields that little t type synthesizes to big T.
Yes. Well, yeah. But now we're not going to put T, now we're going to put a different one. Now we're going to put, let's say, W. And then in the same context, now the context will be relevant for checking when things are equivalent. We check if T is equivalent to W.
Okay, just that.
And if we actually look at this, we can consider the following things. So suppose that we have our definitions of ID and ID type. Consider, for example, for all A in type A, this is a well-formed type. And then we can also consider for all A in type. And then instead of having A, we'll take ID, apply it to, let's say, type. So now this is the identity function on types, and we'll apply it to the type A. And that should give me A again, if I compute them, right? But if we look at our form of weak reduction right now, weak reduction will not reduce this. So what we actually need to do here is that this is full reduction. This recursively reduces every single possible sub-expression, not just the top level reduction. So that, for example, these two types would be considered equivalents. Here, the evaluation order is a bit unclear. You can evaluate terms not just at the top level, but you also evaluate sub-expressions. And it turns out that evaluation order does not matter if the terms are well typed. So there's another function, strong reduction, which is used when applying the turn rule. So this is an explanation of how computation enters the proof assistance. We use computation to before pattern matching against types, and pattern matching against types also includes alpha equivalence. For example, here I've explicitly written that the variable x here matches up with the variable x here. So weak reduction also includes alpha equivalence. Although that doesn't appear in the definition of weak reduction, here we'll have alpha equivalence. The implementation will have that. Okay, so that covers the first thing that I wanted to cover today, which is an explanation of where computation comes in. And in order to actually have computation come in, we wrote several functions. The functions that we wrote, which will be available in the proof starter code, are now we have a function for substitution. So what I rather would like to say is when extending, Proust for predicate logic, you must modify a fairly large number of functions. So now types and terms are mixed, so there's only one parse function as opposed to parse term and parse type. Parsing. Then there's pretty printing. I guess the inverse of type of parsing. Then there's substitution. And then in the goal of substitution, there was this free-in function, which checks whether a variable is free in a given term. It needs to recursively check inside of the term. So if we add more grammar constructs, it'll actually have to make recursive checks in those terms as well. Then there was alpha equivalence. And then there was strong reduction. Well, strong reduce. And finally, there's type checking and type synthesis. So both of these, now all of these 8 functions recursively go through terms. And it's a bit painful, but whenever you add new grammar constructs, you have to add recursive checks on all of them. And for a lot of them, it's going to be pretty tedious. But the most interesting cases are, of course, going to be when you look at strong reduction for many of them, and also type checking and type synthesis. Parsing and pretty printing are fairly rote. Substitution, well, lambdas are really the special case, and then for alls, where you actually have to do renaming. For all of the other expressions, it's just going to be substitute recursively in the body in each sub-expression, just as with substituting for applications. Similarly, free in and similarly alpha equivalents. But those are the functions that came up when we had to implement all of this. Okay, any questions? So now let's get on to the real material. Let's actually start by extending Proust. So we're going to assume that the fragment with for all works. Start with a working version of Proust that handles universal quantification, that handles for all. And definitions correctly. Now, what would we like to add to this version of Proust? Here is our logic wish list. So what are some things that I said that we'd like to have in our proof assistance?
I guess we'd like both types of reductions weak and strong.
Oh, so that was subsumed when I said working version of Proust. So in order to handle for alls, where you can quantify over types, you actually need to have reduction in order for that to work. If we already understand, for example, applying a function to a type as meaning the results of that type. If we consider those types the same, then we have to have that in a working version.
I guess that also means we have equivalence as well already.
Say that again, I didn't hear it.
Does that mean we also already have equivalence in this Proust?
We have equivalence, yes. So this has reduction, substitution, and alpha equivalence. And general equivalence. And definition lookups. Okay, what else do we want? Think about the results that we are trying to prove. We're trying to prove the results that we showed at the beginning of class, right? So for example, for all nats n plus zn equals n, right?
Yeah.
What do we need to give something like this?
I guess we already have the structures necessary, but is equivalence the same thing as just having equal sign?
It isn't. So we don't
Oh.
have equality yet. We
Yeah.
should add equality.
Yeah. And I guess that in turn would necessitate substitution.
We already have substitution,
Okay.
but we don't have equality.
Okay.
So equality types. We'd actually like to form equality in the statement of propositions, right? So right now, there's no way to write an equality in the statement of a proposition. We can't talk about logic in this language. Sorry, we can't talk about equality in this language at the moment, in the actual terms that specify the types. Well, we don't have numbers either, right? Yet, so we'd like numbers, right?
Yeah. Thought numbers came with proofs. I mean, came with racket or something.
Oh, Proust only has what we have right now. So we have a full grammar for Proust at the moment, right?
So we just need to make a structure for gnats then?
Yes, so we need gnats. And let's also do Booleans.
Yeah.
Although we don't need it for this proposition. And as at a later stage, we could also desire existential quantification. And for existential quantification, this would be, for example, there exists an n in gnats. So that's, let's say, times 2, or rather, so that's plus n equals, let's say, this m. So this is the statement where m is a free variable, that m is even, for example. But that can happen later. That's going to be the last thing that we do. So let's handle them in reverse order. Let's first do Booleans, which are a simpler structure than gnats, and then equality. Does that make sense?
Yes.
So first, let's add Booleans. So what was our definition of Booleans before?
They want like the grammar of Booleans?
Yes.
Okay, so it's just true or false, or if bool, bool. I mean, no.
That's correct for conditional expressions, but Booleans themselves are either just true or false.
Okay. Because the conditional would just evaluate the true or false anyway, so it wouldn't be that necessary, I guess.
I don't hear you again.
Because I guess the conditional would have just evaluated the true or false anyways, so it wouldn't be that necessary. Also, we probably need some sort of expressions which we wouldn't find outside the grammar, so that'd be messy.
So we had but you're right in that we also had expressions were either in this language of conditional expressions, they were either Booleans or what? You said it before.
Conditionals. So that's like if expr, expr.
Mm-hmm. Who has a dog? I hear a dog.
Oh, sorry.
Don't worry about it. You can unmute yourself repeatedly. That's fine. Right. So Boolean now this was before. Now, in our current worlds, so let's recap. Current state of our grammar. So this is everything that we're allowed to do in Proust at the moment. And I'll write it in terms of T's. So a T is either, this really should be EXPR, but EXPR takes a very long time to write because I'm about to write it many, many times. A term is either a variable, an application, sorry, let's do an abstraction first, or an application, or it's just the constant type, or it's an arrow, or it's a for all. Or I guess it's all can also be an annotation. So, okay, this is our grammar so far. Now, we would like to add to this the following things. We add so to indicate that we're adding something, I'm going to write it like this. So first I'm going to write dot an ellipsis to mean everything that we had before. And then I'm going to introduce the new constructions that we have. So first off, we're going to introduce a new type called Bool. Then we're going to introduce two constants, true and false. And I'm not going to tell you what the last thing is right at the moment, although it's basically going to be something analogous to an if statement. And for every new construct that we add, we have a new typing rule. So the new typing rules are actually, they're fairly simple. For example, what can we say about Bool? We can synthesize its type to be what?
True or false?
Those are the terms of type Boolean, but what is the type of Bool itself?
It's a type?
Yes. Also, thank you for tuning in. Okay.
I apologize, Professor. I just had another test right before this class, so
okay, don't worry about it. But yes. Okay, now what about true? What is its type?
Well, I guess it could also just be type.
It shouldn't be type actually. What else makes sense?
Oh, can I say Boolean?
Yes. So that's just another type that we've just added to our language, Bool. And Bool is going to be the type of both true and false. So we've added at the moment 3 new grammar constructs, and the rules corresponding to them are very simple. They're just synthesis rules with no premises. So a Boolean these 2 rules right here are variants of the introduction rule for Booleans. So in order to get something of type Booleans, you have 2 ways to form terms of type Boolean. You can either write true or you can write false. So these are the introduction rules for Booleans. And there's also an elimination rule for Booleans. So how do you use a Boolean? So we need a new grammar construct. It was suggested before that we should have something analogous to an if statement. So what does an if statement look like? Let's figure out what the logic version of it should be. It's more general than just if.
Well, it's probably going to be 3 branches of that logic.
So if you're given a Boolean, you can, if it's true, you do something. If it's false, you do something else, right?
Yes.
Now, there are types. So for example, in some programming languages, the following statement will be illegal. You won't be able to say, write something like if true, and then let's say you produce a natural number for one of the cases, and then you produce a Boolean in another case. So here you have mixed types in the true statement. But in our language, we have dependent types. So for example, we can write statements of the form for all nats n equals n. Now here, if you think of a term of this type, then it's a function. And if you give it a natural number, it'll give a specialized proof term. And the results depends on the inputs. So in general, we're able to have results that depend on input. We actually have a construct that lets us have mixed types so long as we say what the types are. Now, if you think about what the eliminator statement is, it should allow us to prove a statement that's quantified over for alls. For all Bool. How do you prove, let's say this is some statement P that, let's say this is some statement T that might involve B. How would we prove a statement for all Booleans?
Can we create a function that takes b then returns t, something like that?
Well, so let's think about the case for natural numbers. There were 2 ways to prove for all statements for natural numbers, right? What were the 2 ways?
Induction?
Yes. There was structural induction. And the other one was?
The anonymous method?
Yes.
Or have, yeah.
And the idea behind the anonymous method was that you didn't assume anything about the structure of the argument that you were passed. And the anonymous method was, the rule for that was lambdas. You assumed something, you bound, let's say, a Boolean to be, and then you try to do something with it. but then that Boolean would be anonymous and you wouldn't know anything about it. But here we actually have a grammar for Boolean values. A Boolean value is either true or false. So there should be an analog of structural induction for Booleans as a second way of proving for all statements that relies on the structure of Booleans. So what is the structural induction principle for Booleans? How do you prove something for all Booleans?
Well, there are only two cases to consider, true or
Right.
false.
So what do you do then?
I guess you can type check. Well, type check true and false to something.
Well, so let's say the statement, the statement might in general involve B. So for example, let's say that we have equality, which we don't have yet. For all Booleans, let's say our statement is B equals B. Now, a way to prove it is to use reflexivity of equality, and then we can use the anonymous method. But suppose we want to prove it by structural induction. Then we would prove it how? We would provide a special proof for what?
A special proof for true and false.
Yes. So for true, what statement are we trying to prove?
We're trying to prove that true implies true equals true.
Well, true equals true is a type, so that's a logical statement, right? True equals true makes sense as a logical statement, right?
Yes.
You can ask about proving true equals true, but you can't say true implies something because you can't prove the true itself has no terms. So the logical statement is true equals true, right?
Okay.
So you can prove true equals true. To prove this, we prove true equals true and false equals false, right?
Okay, yeah, because if we're just considering separate cases, we don't need the for all initially, and it would just be the statement at the end, right?
Yes, exactly. So if we look at what the structure of a Bool value is, then it's either true or false. So if we want to prove a statement for all Booleans, we can prove the statement for true and we can prove the statement for false.
Yeah.
This is sort of a very simple structural induction principle, simpler than the one that we had for natural numbers, right?
Yeah.
For the natural number, there was a case in the induction principle for every single variance in the grammar, right? So in the same way that natural numbers had two variants in the grammars, Booleans have two variants in the grammar. And so for each one of those variants, there is a case that you have to prove in order to prove a for all statement for Booleans.
Here, the cases are actually well defined, as opposed to like in natural numbers, we had to define it in terms of itself in the second case.
Yes, there was an implication in the second case. And we're going to see that momentarily when we do natural numbers. So the induction principle for natural numbers is going to have a much more complicated second case, right? So then let me ask this question. How was the statement that we were trying to prove was this, right?
Yes.
What type does this have? Or no, rather, how do I determine what statement I'm proving for true and what statement I'm proving for false? That's a vague question, but can you give me a construction that takes a Boolean and returns a logical statement?
Well, in this case, we have an equality type, right?
Right.
So, I guess
but how do I make a construction that takes a Boolean and returns an equality type?
Well,
So that's vague. I'm not sure if I'm motivating it correctly, but we can write lambda, let's say x, and then x equals x.
Okay.
So this is a function. What type does this function have?
I guess an arbitrary type, whatever type x happens to be.
That is true, but we'd like to type it where x actually takes a Boolean.
Okay, so I guess we can just set it to a Boolean for now.
So Boolean, let's say it takes a Boolean argument,
Yeah.
and then what does it return?
Equality.
But an equality type is a type.
Oh. Okay.
So this is a function. If we think of types as logical statements, this is a function that takes a Boolean and returns a logical statement. So for example, we could take this function and we could evaluate it on true, and then we get true equals true. And if we evaluate it on false, we get false equals false. And a thing like this, a term of type bool to type, is known as a property of Booleans. So here, there is a difference between writing a for all statement and writing a lambda function. The lambda function is a construction that produces propositions. The for all statement is just a statement that for all Booleans that holds. So in general, when we'd like to prove a for all statement, the first thing that we should say is how to build the statement. So our eliminator for Booleans, the first thing that it's going to take is it's going to take a property. So the property is something that's going to get referenced to later. So let's say we take something P of type bool to type. So if I have a property, and I'd like to prove a for all statement that has those types in it, then what do I need? We said it before. You need to prove what?
P true and P
Yes.
false.
So you take P true and you apply P to true. That gives you the statement that you want to prove it for the true case, and then you give a proof of this property in the false case. And then if you've provided both of those, what have you proven?
That
For all bools.
Yes. That's
That was the type.
that what?
Type.
Well, you're more specifically, think about it as if you were for all, well, you should prove, what did we prove here? Here we proved for all B in bool, B equals B, right?
Yes.
The conclusion wasn't just type, it was B equals.
It was the statement itself.
Right.
So,
and so how do we give the statement for an arbitrary Boolean?
I guess in this case, we call the statement P, right?
So we take P and we plug what into it?
B.
Yes. So this right here should be the structure of the, this is the eliminator for Booleans. This should be the type of the Boolean eliminator. So the Boolean eliminator is some construction that takes a property that you're trying to prove. You give it a proof in the true case, you give it a proof in the false case, and then you get a construction that whenever you pass it a Boolean, it returns a proof of the respective case. So if we actually look at this, there are four inputs that it takes. The first input that it takes is the property, then it takes a proof of true, then it takes a proof of false, and then it also takes a Boolean B, right? And then it eventually gives you P of B. So we are going to take this and we are going to encode it in a 4-term structure. And this is going to be called the induction principle for Booleans. And it takes 4 terms. And the meaning of those terms are as specified here. So the first one is a property of Booleans. The next 2 are proofs in the true and false case. And the last one is the Boolean that you actually want to use to eliminate it on. So for example, with only the first 3 arguments, we would have proven a statement for all B in Bool P of B. And then now in order to use that statement, you supply a 4th argument. If we actually wanted to make something in which you could supply the arguments one by one, you could take that eliminator and you could put a bunch of lambdas in front of it. So then what's the typing rule? Let's suppose that we have gamma and we have a term that says the Bool induction. And let's call the first argument P. Let's call the second argument proof of true, proof of false, and then Boolean. So this will type synthesize to type what?
P of B.
Yes. And then in order to see that it synthesizes that type, I need to check a few things. And the things that I'm checking can just be read off from the type. So what's the first thing that I need to check?
P?
Yes, that P has what? Type.
Bool to type.
Yep. And PT is supposed to have type.
True.
Sorry, I didn't hear you.
Yes, true. And PTN.
Well, it's supposed to be a proof of P true, right?
Yeah. And
It's not. So I couldn't write true here because true isn't a type, right? But I can get a type by writing P true, right?
Oh, okay. Yeah.
And then similarly, PF should type check to what?
P false.
Yes. And B should type check to?
Bool.
Yes. So this is perhaps the most boring type synthesis rule that we have. We just check that the things that we're passing it are the right types. But what's harder to remember is the eliminator. But what does the eliminator say? It really says, give me a property of Booleans. I want to establish that this property holds for all Booleans. How do I do that? Well, what is a Boolean? A Boolean is either true or false. So I prove it in the true case, I prove in the false case. And then I get a construction that whenever you give it any Boolean, it gives a specialized proof term to that Boolean. Now, here's the cool thing. You can also, so let's write it turns out that induction includes recursion. It also lets us define functions. So let's define the AND function. So AND should be a function that it should be a function that takes two Booleans and returns a third Boolean. And I'm claiming that I can define AND using the Bool induction principle. How do I do that?
So this function should have two arguments.
Yes. So what do we start with?
We have start with like two booleans.
Well, I mean, we're writing the proof term. So
Okay.
we're writing a term of, we're writing AND. We're writing something of this type. So we'd like to write a function that consumes two Booleans and produces a Boolean, right? How do I start writing the function?
Start with lambda, I think.
Sure. Let's call
Lambda.
the two arguments A and B.
Okay.
Now what?
Then C.
A third argument?
Not an argument, but a result. So
Yeah.
the application of A and B. I mean, what can I say? It's like a function. Then
How
it's
do
like
you use
A, B.
Booleans?
How do I use booleans? The eliminator.
Yes. So let's write a Bool, an eliminator. The induction principle. Now, what should I put for P? So whatever P is, the eliminator is going to produce something of type P applied to something. What do I always want it to produce?
Oh, we want to produce an application. What?
But I mean, it will produce P of B, but we'd like to always produce a Boolean, right? So if we look at this Bool induction term, what type does it have? It'll synthesize to type P of B, right? But we'd like its type to synthesize to Bool, right? Because we want to define a function Bool to Bool to Bool, right? So we've taken two Bools and we want to produce a Boolean. So what should P be?
Can you give some examples of P?
Sure. So one example of P is lambda x equals x. So that produces a type, right? X equals x. So we haven't talked about equality yet, but x equals x is a type. So it should be some function that takes a parameter and then returns a type. In this case, if we looked at x equals x, then depending on the Boolean that you returned, gave it for B, you'd either get true equals true or false equals false, right? And those are different results types. But here we want the results type to always be what?
A Boolean.
So how do I write that? So it needs to be P has to have type Bool to type.
P has to have type Bool to type. And we
Why?
want
because look at the typing rule. In order for a Boolean to be well typed, you have to type check P against Bool's type, right? Go ahead.
And we want that P to return a bool. Right?
To return Bool itself, not a Bool, but Bool.
Bool itself. So P has to be bool to bool.
No, it has to be Bool to type, but but Bool is a type.
Yeah, so we've narrowed down that type down to bool.
Right.
Okay. Is that lambda x dot x, something like that? But
lambda
this
x dot what? X takes a Boolean, and then it should return a type.
takes a Boolean, returns a type, and that type should be bool.
Yes, exactly. So no matter what Boolean you give it, the result is going to be a Boolean. That does not depend on x, right?
I see. So we can just write bool here, no matter what that bool is.
Yes.
Okay.
So now we're going to write something here. So here, let's say this is the true case. This is the false case. And then we're going to actually give it a Boolean. We have two Booleans in our hands, right? A and B. Which one should we use the eliminator on? Choose.
B.
Sure. So if B is true, then what's the results? So now we say what the output should be if B is true and if B is false. So if B is true, then what?
If B is true, then if A is true, it should return true.
Right. And so what's another way to write what you should return then? If A is true, you return true. If A is false, you return false. In other words, you're returning
A and AB.
well, for this case.
A itself.
Yes, A itself.
Huh.
If B is true, then the result of the AND statement is just whatever A is, right? And if B is false, then what do you return?
Still return A.
That would be true if you had OR. Well, it would be the other way around for OR. If you have an AND statement and B is false, then what do you know about the results?
It has to be false. So we return false. Yeah.
So this is an example of a structurally recursive definition of the AND function on Booleans. This is structural recursion coming from the principle of structural induction. And so now we see what the relationship, well, it's going to be more evident for numbers. So when we define natural numbers, we're going to be able to define plus in this way. But this is an example of a structurally recursive definition using an induction principle.
Oh wait, why is the third argument false?
So
we say it was like B or something.
Say it again.
Then we say the third argument was B or something.
Oh, well, so if this is what happened, where we return if B is false. If B is false, we return false. But if B is false, then we could also just return B as well, right? Is that what you're saying? You'd be happy if I wrote this?
Actually, no, I think the false would be all right.
But they're the same.
Okay.
But I prefer to write it like this, because, for example, B might not be computationally reduced. And we should just return already the computationally reduced version.
Okay.
And so what we've constructed here, if we try and type it, it's a function from Bool to Bool And then no matter what, it returns P of B, and that's always Bool. So let's try and see. Oh, okay. I guess let's also define or. What if? How do we define or? What do I do?
We still need to use bool in.
Yep.
Then it should also takes a lambda. It should also takes x, then returns a bool.
Well, Bool, not a Bool. Bool.
Not that returns bool.
Right.
Then
Now
we
let's
can let's apply it on B. Say.
Yep.
So if B is true, it should return true.
Good.
If B is false, we should return A.
Good. Perfect. So this is examples of how we can make recursive definitions using the inductive principle. So our language of logic already lets us define and or for Booleans, which is different from and or for logical statements. Because there, the meaning of and or isn't the Boolean interpretation, it's in terms of provability. So, okay, so into our language, we've added 4 new constructs. One is Bool, the type Bool, then the 2 introduction rules, and then 1 elimination rule. And the elimination rule lets us, for example, construct functions by structural recursion. Well, I say structural recursion now, it's going to be more evident when we have natural numbers. But okay, there's one final thing that I need to talk about, and that's what is the computational meaning of a Boolean eliminator? So how do you strong reduce this? What's the reduction? So strong reduction. So if I have a Bool int p proof of true, proof of false, and then Bool b. Assume that this is well typed. Assume this type checks. What should this reduce to computationally?
To a bool. To a bool.
Well, what Bool? To what Bool? So we know that, for example, it has to reduce to something whose type is P of B, right?
Yes.
But that depends on what B is, right?
Yeah, would also depend on what P is.
Yes, it depends on what P is and also what B is. Well, it depends on all 4 terms, in fact. But let's suppose here. Let's suppose that B is true. Then what does this reduce to?
PT.
Yes. And similarly, if we know that it's false,
And it's PF.
then it should reduce to PF. So in general, the reduction principle should be that you reduce B and you see whether it gets down to true or false. It doesn't always have to get down to true or false. For example, it might just be a variable. We don't know what it is, in which case we can't proceed further. But if we can reduce B down to a Boolean value, then the strong reduction principle should just replace the entire Bool ind principle with the specialized proof for true and false, right? So that's basically like if true and if false rules, but now they apply to cases where there are also variables, which we don't know at the moment if they're true and false. Do you see the example that I mean? You can have, for example, something like lambda b, and then you can have this Bool ind principle. Then when you're doing the reduction, you'll have B in the context with type Boolean, but you don't know if it's true and false. So you can't reduce that further, right?
Yeah, you need to know B to reduce.
So let's look at the code for everything here. So this is a version, and this is the version that you'll be using as your starter code, although there are some mistakes in it and they might need correction. Oh, here is actually, this is what we were doing before. So this version has Booleans. It has Bool, true, false, and the Bool induction principle, which takes 4 arguments. And then it has AST nodes for each of these. Then it has parsing, pretty printing, substitution, free in. All of these have each one of these new constructs in it. Alpha equivalence also has all of these constructs in it. Weak reduction doesn't have it because it only handles these cases, but strong reduction also has it. So here, look at how strong reduction works for the Bool induction principle. You try and strong reduce B, then you try and match it. And then if the result of strong reduction is true, then the entire Boolean principle just reduces to the strong reduction of the proof of true. And here, the proof of false. Otherwise, if you can't get it down to one of these forms, then it's still going to be Bool induction principle, but you may as well take all of the other 3 things and reduce them further. And then BR is already reduced. And then for the actual true, false, and Bool, well, there's no computation that you can perform on those. But the induction principle for Booleans does have computational meaning. Then if we look at what the rules are, well, there are no rules for type checking for these constructs. But for type synthesis, true synthesizes type Bool, false synthesizes type Bool, Bool synthesizes type. And for the Bool induction principle, what do? We basically type check all of the things. And then we return application of P to B. And there's a weak reduction here, although you don't need that weak reduction there. So let's try and do some definitions. We have global definitions, right? So we can try and make define, let's say and. And then what was our term for and? What was our proof term?
Lambda A, lambda B, Bool induction.
Yes. Now let me just check one thing. In the grammar, we use a lowercase letter for the Proust grammar. Okay, then what? Then we need the property, right? What was the property?
So lambda x.
Then what are we always producing?
A Bool. Not a Bool, but Bool.
Yes.
Wait, not a Bool, but Bool.
Yes,
Yeah.
You're always producing something of type Bool, but the function always returns Bool.
Yeah.
This function always returns Bool, whereas the Boolean induction principle, when it's fully evaluated, returns a Bool. Okay, so what happens if B, we're applying the induction principle on B. And what happens in the true case?
In the true case, it returns A.
And in the false case?
It returns false.
So that's our term. And we're going to say what type it has, because otherwise it doesn't know what A and B are, right? So in order for this to make sense, we also need to provide the type here. By the way, when you're making definitions here, if you can press enter, return, and it will actually not run the definition unless all the parentheses are matched. It'll let you do multi-line definitions in here. So this should have type bool to bool to bool. And it succeeds. So that type checks. And then we can write things like, so we want to, well, so first off, we can write parse expr. And then we can write, for example, things like, and let's say true false or true true. So that's an application and onto these two things. Now we can type synthesize that in the empty context. And what do we get? What's the type of and's true true?
A type?
Yeah. Well, no, of and true true.
And true true. It's a bool?
Yes. And now if we take that expression, we can also strong reduce it, right? So this will actually perform computation in the empty context of that. And then what do I get? Oh, well, I don't need this.
Just get true.
Oh, if I type strong reduce correctly, then you get yes. ST. There we are. You get true. So, okay, look, we added, so what did we need to do to add Booleans? We added some AST nodes. We did very rote additions to each of these functions, parsing, pretty printing, etc. What were the interesting cases? The interesting cases were the strong reduction rule that actually let us reduce this computation to this results. And then there was really the type checking rule for the Bool induction principle. And then all of the other rules were very simple. This rule was tricky and we needed to figure out what it was. And then this rule was tricky. So the only non-boilerplate code was this block of code and this block of code. These two blocks of codes have added Booleans to our logical language. We can define or then, for example. How do we define or?
Still given two inputs, A and B.
Mm-hmm.
Then we do Bool induction. The P should be lambda x, yep, and returns Bool.
I could have typed that. Then we're applying this, let's say, to B. If B is true, then
we return true.
Yep, and otherwise?
We return A.
Yep. Then let's also give it that explicit type. Okay, bam. Or
it should be should not be capitalized, the Bool in.
Yes. Thank you. Very good. That's exactly the issue. Okay, bam, we have or. Then we can say, for example, strong reduce, let's say, or true false. What do I get?
Yes, false.
Nope.
True.
Yes. If I copy the right line again. And then false, false, if I do false, false.
That's false.
Okay. So this is how we make recursive definitions. You don't, this doesn't only let you prove theorems for all Booleans, it also lets you define functions on all Booleans. So if we were proving theorems, we'd call that an inductive proof. If we're constructing functions, we'd call it a recursive definition. But here you see that there's a relationship between inductive definitions of functions and inductive proofs of theorems and recursive definitions of functions. They're all accompanied by the induction principle on Booleans. And that's just an encoding of what the structure of a Boolean is. A Boolean is either true or false. And because of that idea, we get a proof rule. And that proof rule, because we're working in higher order logic, also lets us define functions on Booleans. So the induction principle is also a recursion principle. And really, the only thing that we needed to do, the only clever lines that we wrote, were this block of code for type synthesis and this block of code for strong reduction. Those ideas encode Booleans into the language. But in order to get there, there was a lot of really subtle things about this proof assistance and how we set everything up. But once we've set everything up, we can add Booleans pretty easily. So now we're going to do natural numbers. Any questions about that? So let's take a break before we do natural numbers, but you can sort of get the sense of how natural numbers are going to work as well, right?
Yeah.
So let's take a break until 3:40. Resume at 3:40. Maybe command minus, and then you can see, for example, the definition of or here. Okay, see you in 5 minutes. Okay, so are we all back? Okay, so number time. Natural numbers. So before, to remind you what we had the following starting grammar in the language. We had just lambda calculus terms, and then in general we typed them with for all types. And we had type as a grammar construct, arrows for alls, and annotations. Then we added Booleans. For Booleans, we added the type of Booleans, two introduction rules corresponding to the two variants in the grammar of Booleans, and an induction principle, which served as an eliminator for Booleans. So for natural numbers, we're going to have to say, well, nat is going to be a new type that we add. Then we're going to write down what the grammar for natural numbers is, and we're going to add corresponding terms for the constructors of natural numbers, the introduction rules. And then we're going to write an eliminator for natural numbers, which is going to encode the induction principle of natural numbers, structural induction. Okay, here we are. So in which case, what is a nat? Let's write down the grammar for natural numbers. This is now a grammar. A nat is either what?
Z or S of a Z.
Yes.
S of a nat.
So that suggests that for our grammar of terms, we are going to add to it. So the way, well, so that's the ellipsis, and then I'm going to add 4 items. The first, let's say, is literally the type nat. Then what are the next 2 items?
Z.
Yes. And?
S.
And then I write what here?
Something like a predecessor?
Well, it's going to be a term in general, right? An expression.
Yeah.
And then the last thing is going to be nat induction. And we're going to see how many things that has. Although, can you guess how many things that has?
4.
Why?
It should have a P that is a property.
Mm-hmm.
Then it should have a proof for the 0 case. Not 0, but natural number should start with 1, right? But like with the basic case. Then for a more advanced case where we have the proof, then we are trying to deduce that for a k plus 1. Then we have like a Z, something like that.
And then the thing that we're using it on. And exactly, so that's exactly right. And another way to say it is that nat has as many grammar variants as does Bool, right?
Yes.
You have the property, then you have one case for each grammar variant, and then you have the thing to which you're actually applying it on, the actual natural number that you're eliminating on. And then we can write down what the typing rules are. So what is the typing rule for nat? We can synthesize its type to what?
To type?
Yes. Now, what about Z?
It should be synthesized to nat.
Good. So those are the 2 basic rules. Now, what about an expression of the form S of n? Let's write S of k. What type will this have, and does it have any premises?
I mean, K should be a not, right?
Yes. So there's one premises we need to know that K, let's say, type checks to nuts.
Then S of K should be a not.
Good. So because there's a sub-expression, in order to check that a certain grammatical expression indeed defines a not, you have to recursively check that the subterm that it's a successor of is also a not. Okay, and then let's just write down what the induction principle is. So first off, we start off with what? What's the first thing that we need? We need a property. And what's the type of that property?
Given a not, that returns type.
Good. Then what do I need?
We apply this P on Z.
Good. So I need a proof of Z. Then I need, what else?
For all K that is a not.
Good.
P applied on K implies P applied on S of K.
Perfect. And then what does that let me conclude?
That for all nats N, P of N.
And that is the type of the induction principle for natural numbers. So this is the induction principle on natural numbers. And what does this say? This says if you want to prove some property holds of all natural numbers, you need to prove that it holds for Z, and you need to prove that it holds, if it holds of K, then it also holds of S of K. Now, unlike the informal rules, we actually have to say what K is. We need to have K, and actually, no, it was the same. It was for all, and then P of K implies P of S of K. Except now for all statements, our hypothetical reasoning is also handled by lambdas. So it's exactly the same as what we had before. And then, so that also tells us what the typing rule is for terms of the form not ins. So if we have gamma and we have a term that says not int, and then what should I call the arguments? What are good variables to use?
The first argument should still be P.
Mm-hmm.
Then the proof in the case of Z.
Mm-hmm. Let's say lowercase letters. Then well, P and your choice.
I don't know.
Let's call it P successor. But let's write, we also like short names. Let's write S P S. That's short, right?
Yes.
And then the natural number should be called
N, I suppose.
So this will synthesize type what?
P of N.
Good. And now we write what the premises are, which is somewhat tedious, but let's write them once. Okay. P should
Type checks to arrow,
Mhm.
arrow type. That should be, that is net implies type.
Then
PZ should be type checks to PZ.
good. Okay, now this is where it gets scrunched up. I'm going to try and write this. Okay.
That is P applied on.
No, it's not.
No, it's not. Okay. It's sort of a implication. That is P of well, what? K?
What is K?
K is a NAT.
So what do we start with?
Start with. I mean, I think it should be like P of something implies P of the successor of something.
The successor, but what is the something? We need to quantify over the something, right? So think about informal proofs that we did at the start of the class. You wrote a to prove statement, right? What was the to prove in the inductive case?
Okay.
Well, we have it written immediately above, right?
Yes, that's for all K. Oh, we define K to be a NAT.
Yes.
Yeah, for all. Okay, yeah, P of K implies P of S of K.
Mm-hmm. Those are two closing parentheses. And then also, I guess the final thing we need to check is
whether N type checks to NAT.
good. Okay, so that is the induction principle. Now let's do strong reduction first. So here is the strong reduction rule. So if you have an expression of the form nat int p pz, and we assume that before we do strong reduction, we assume that this type checks. So we assume that this is a well-formed expression. And then let's say we have the case z. Then what does that reduce to?
Should return reduce to pz.
Yep. And in the other case, if it's some successor of, let's say, k. Here's the tricky part. Think about what type PS has.
PS is a for all statement.
Right.
That is an implication. So we would do PS first, then recursively call.
What do we apply PS on, right?
Yeah, NAT int. Then instead of doing it on S of K, we do it on K.
Well, let's look at what P and is. It takes two arguments, right? The first argument is K and the second is P of K.
Yeah.
So what's the first argument?
K.
Then that returns the implication, something of this type, right?
Hmm.
And what do we apply that on?
That on the net in.
Good.
The P, PZ, PS, S. No,
Yes.
not K. K. It should be K.
Exactly. And this is structural recursion. The three arguments here go along for the ride. So this is structurally recursive. And then if you reduce the thing in the third position, and if it's Z, you just return PZ. If it's a successor, then you remove the successor, and then you apply the function that lets you go from one case to the other, and then you recursively reduce the case on. So this isn't fully reduced. You might have to reduce more. K might also be a successor, and then you keep going. But these two terms are equivalent computationally. So I'm now going to give you something that was going to be part of the assignment, but I guess we'll just do it for free. So you will have to implement natural numbers yourself. But you see how it's implemented with Booleans, and natural numbers are similar to Booleans. So you just mirror it. But let's define plus. So plus should have type what?
Not? No, it should be a function, something like lambda.
Oh, no, it's type. A lambda is a term. What is the type of plus?
It should be a not. Plus, no.
Well, it's a function. It takes a not and then?
And takes a not, then another not, then returns a not.
Good. This is similar to and or. They were bool to bool to bool. So let's define it. So let's give a definition. Let's say the numbers are n and m. Lambda n, lambda m. And then what?
Then we check. Oh, we do a net in.
Exactly. What's p?
What's p? It should be a lambda function. Lambda x, and returns a not. Not a not, but not.
Not. Yeah, exactly. Then let's say we're applying the recursion principle on what? On.
So does this mean plus an m or mn?
Well, n is the first argument, m is the second argument.
I see. So we'd better apply it on m, so it would be consistent
Yes.
with the rule that we previously defined.
Exactly.
So yeah, so if m is z, that should return n.
Good.
If m is s of a not, it should be s of plus. I mean, we check whether
the type that we need to provide.
Yeah, we need to provide that M is it looks like a S of something, some S of
So
K.
it should be, what type do we want this thing to have? Let's write down that type. For all,
S for all M.
not M. M and N are already used.
For all, just will. It can be anything, right?
Yes.
I don't know.
K
Okay.
in
For all in S.
S.
Not in S, but not.
Yep. And it should be before, it should be something P of K to P of S of K, right?
Yeah.
But what are P and K and P of S of K?
It's what are K?
So in
Wait.
our case, what is P of K when K is an at? This is the same as
PS? No.
But what was our P in the case of plus? It
In the
takes
case
anything
of-
and it returns what?
Not.
Yes. So in other words, in the induction principle, this thing has to be of type for all K and not P of K implies P of S of K, right?
Yeah.
So here it should be for all K and not what?
It's not P of K implies PS of K.
We can write it like that, but we can also write it as
Plus? Can we use plus? No.
no, that's what we're defining. Okay, instead of writing P of K, we can write what?
Instead of.
Because we know what P is. P always
Oh.
just returns not, right? So here in this case, we want to take K and then
Not.
return what?
Then yeah, that will be S of a not
So not to
P of S of K. That
which
should
is
be
also
which is also um,
well, P of anything is what?
P of anything is a not,
Is not a not, just not.
but not. Then P of S of K should also be a not. Huh. Oh,
It should also be not.
should be not. The type
Yes.
not.
Exactly. So what we want to put here is roughly a function of two arguments, right?
Yeah.
So
Okay.
let's write that.
Yeah, it's gonna be lambda something. Lambda
K.
y. Lambda k.
It's better to have these match up.
Okay. It's a brand new function. Okay. It should also return not. No.
Well, so the first thing that it takes, let's see what this is. This is P of K, right? So this should be so here we're assuming that M has the form S of K, right?
Yeah.
So then this argument right here, it represents P of K, that's the type, but the term specifically is what the value of plus NK is, right?
Okay.
So that's the results so far. Let's call this maybe y. So y represents the recursive call. Y represents plus nk. And we're trying to define plus ns of k, right?
Yeah.
So think about P, still think about it as proving a theorem. Writing a function is the same as proving a theorem. We're trying to give a correct definition for all natural numbers m, right? What is the correct definition if m is z of plus?
Correct definition. Could you repeat what you just said?
So we're trying to define plus nm for all natural numbers, right?
Yes.
So let's suppose that m is z. Then what is plus nz?
That's n.
Right. Now, in the other case, suppose that m is s of k, right?
Yeah. Yeah.
Now, assume that we've solved the problem for k. In other words, assume that we've already defined plus nk, right?
Yeah.
Then how do I define plus ns of k?
That will be s of plus nk.
Yes, and the variable which I use to refer to plus nk is what?
Y.
So this should be s of,
S of y.
yep.
Huh. I see.
So
So that k
is-
represents for all k that is not. What does k represent?
k, k is, m has the form s of k.
I see. I see. Okay.
So if we think about it as theorems, so now I'd be tempted to prove something like, oh, here, let's actually, well, that's by the anonymous method. The simplest proposition that you can prove by structural induction is plus z, plus zn equals n, right? But that's the main homework problem that you're supposed to do.
Oh.
So I don't want to show you how to do that. But if you think about it as, think about defining functions as proving theorems. In proving a theorem, you're trying to establish the theorem for every case. In defining a function, you're trying to define the function for every case, right?
Yes.
So this is how you go from the definition of plus nk to plus ns of k.
Okay.
Now, you assume that you have that definition, and that assumption gets bound to something. Now, since this statement is a for all, you also need a lambda to capture that. It may happen, for example, that your definition does use k. Let's actually look at an example of that. Let's define factorial. That's a better example. So consider facts. What type does factorial have? Oh, no. Let's do multiplication first before we do, let's do multiplication. So this should also be not to not to not, right?
Yeah.
And let's just write down the definition informally. This appeared on the midterm. Mults, let's say nz is what?
Is z.
Good. And mults n s of k?
Plus n
Good.
and mult sk. I mean nk.
Yeah. And you see that this definition is also structurally recursive. We've defined what mult n s of k is in terms of mult n k. So it's structurally recursive on the second argument. Now let's define okay, first, so let's give a definition for multiplication. So it should be lambda n, lambda m, and then what?
Still net in.
Mm-hmm.
Still a function that takes lambda x, then returns not.
Mm-hmm.
If we do it on m, if m is z, it should return z.
Mm-hmm.
If m is of the form s of k, then we do lambda k, then lambda y.
Yep.
That is, yeah, y, where y means mode
Yes.
mode in k.
We keep track of that informally, that this represents mults n k. Okay,
And
back to the term.
yeah, we've already defined plus, right?
We have.
Even so that will be plus plus n. Do we have it? Yeah. And then y.
Good. And then we're applying this principle on what?
Apply this principle on m.
Good. So that is the definition of multiplication. And now I needed to define multiplication so that I could define factorial. So let's just give the definition of factorial informally. Factorial of z is what?
Is s of z.
Yes. Good. And factorial s of k?
Should be mode k. No. Mode s of k.
Yes.
Then backed k.
Good. So now let's write the term for it. So it should take a single number, n, and then what?
Then we do net int.
Good.
And similarly, we have lambda x, and it returns not.
Mm-hmm.
And we can only do it on n. If n is z, we return s of z.
Mm-hmm.
If n is of the form s of k, we do lambda k. Then lambda y,
Mm-hmm.
where y means fact k.
Good.
Then we apply it on mode s of k
Good.
and y.
And we see in this case, k actually got used. And then
Yeah.
we're applying this principle on the only thing that we have.
N.
Yeah. So here's an example that actually uses k. Your homework, and I should put that up tonight, will be to add natural numbers. And then once you've added natural numbers, to prove some basic properties, the ones that we had at the beginning of the course, specifically plus Zn. But also one of the problems will be to define addition. And so I guess I've given that to you. But it was worth going through to get used to using the induction principle as recursion principles. And then in the homework, you'll figure out how to do the induction principles as actual theorem proving principles to prove properties about all natural numbers. In that case, the property isn't going to be trivial because the number is actually going to appear in the property. So for example, for your homework, to prove for all, well, how would I state the property plus n plus z?
All n that is a knot, for all nats n, plus implies plus nz equals n.
Right. So now we need to actually discuss equality types. Plus z n equals n. So that's the statements. Now let's discuss equality. And I'm actually going to I'm going to discuss everything about equality except for the strong reduction principle, because I think I'm going to change the strong induction principle in the proof assistance. But apart from giving the strong induction principle, I'll tell you what the strong induction principle currently is. But everything else is going to stay the same for the language. So here is equality. This is the abstract big bad of the course. How do we handle equality? So in one super abstract sense that doesn't come across in this proof assistance, equality is also an inductive data type in the same way that natural numbers and Booleans are. It's an inductive data type over all terms that are equal to a given term, where the inductive construction is how many computational steps away it is from that given term. Now, I'm not going to write a grammar for this, and we're treating computation as sort of being built into the system, but I'm going to tell you directly what we're adding to the language. So first off, to the language of terms, the first thing that we're going to add is equality types. Then we're going to add one single introduction rule, and this is going to be EQ reflexivity. And then we're going to have an equality eliminator. And right now it's called not equality induction, but equality elimination. Although in certain implementations, this could be called equality induction. Now, we don't know how many things it has at the moment, and I'm not going to have you guess because we're going to guess what it is in a second. So there are some number of things. Okay, but first off, let's just give the typing rules for the new type that we've added. So first off, remember that we're trying to form things like, what's the motivation for equality types? The motivation for equality types is that we basically like to have statements like we had before. We'd like to make statements like for all n in nats, that's plus z n equals n. So this is of something that we want to have in logic. So here, n was the nats, that's in our context, and z was a nat. Now, if I have an equality type, let's say t equals, or s, then this is a type. provided what?
T can be synthesized to some sort of proof, and W can be, no, not W, S can be synthesized to something, and we check whether those two synthesized type are equal.
Yes, that's
Not
perfect.
equal, but equivalent. Like
That's basically perfect, but instead of synthesizing both types, I'll just check S against T. That would, for example, if you use the turn rule here, if you use the turn rule, then that would become equivalent, right? So for example, remember that the turn rule, gamma S type checking against T, if you use the turn rule, then that becomes exactly what you said. Right? So what you said was this accepts the turn rule applied to it. Do you see?
yes.
Okay, but this is going to be the rule. Now, what's the key observation about this rule? I mean, what does the rule really say? For example, consider the expression Z equals true. Is that a type?
Yes.
Why?
That because I can synthesize Z to be a bool, and
Yes. Well, no, it's not to be a bool.
not a bool, but true.
True is
I
a
mean,
bool.
true
Z is a not, right?
wait, why is that a not?
Z?
Like, wait, okay.
Z is
Ah,
definitely a not, right?
okay. Then we cannot do that.
Right, because if we do it in the way that you said, where we synthesize both types, then we'd succeed in synthesizing not here
Yeah,
and bool here. And
and those
these
are
are
not
not
unique.
equivalent. So in
Yeah.
other words, this is not a type. So in other words, in order to form an equality type, we need to form an equality type of two terms of the same type. In order to know that an equality type is well formed, we need to have two terms that have successfully been typed in that way. So this is an important point, and it's a very useful point. If we allowed forming of equality types in general, then a lot of bad things would happen. It's much nicer if we only consider equality types when both are terms of the same type. This is important. Okay, let's consider this reflexivity construct. This should be the introduction rule. What type should this synthesize to?
x is equal to x.
Yes. And should there be a hypothesis?
There cannot be a hypothesis.
So would it always be the case then that this would return a valid type?
I think so.
Well, what are the hypotheses for x equals x being a type?
X itself has two type checks to be a type.
Not to be a type, to be anything, right?
Anything. Oh, yeah, because anything is equal to a self.
Yes, but here's the catch. The word anything hides something. Anything is a thing, right?
Yes, it's a
But
thing.
not all grammatical expressions are things. So for example, we can, for example, if we have for alls, then when we have for alls, these are frequently types, right?
Yeah.
So let's say we have for all x, and then let's say we put something meaningless here, lambda yy. So that is not a type, right?
No, it's not a type.
I want to put an arrow here. In other words, if we try to synthesize the type of this, it would fail. So in general, we'd actually do want to have a premises. If we form an equality type, it should be well formed. So what should we check before synthesizing type x equals x?
Whether x can be synthesized to type,
Not type,
but something else.
anything. Let's say
Anything.
t.
Okay.
So it can be any t at all, but it has to synthesize to something. And that's not true for every single grammatical expression. Here's a grammatical expression which doesn't synthesize to anything because it's ill-formed. So that's another thing that we do to guard for things when forming equality types. If we synthesize a type, we always want with the results of synthesis to be well formed. And if we didn't have that premises here, then the result of synthesis would not always be well formed. And by the way, that currently doesn't exist in Proust. That's currently another mistake. But this has to be a premises. So, okay, these are the two constructors that we have so far. So there's the typing rule for when a equality type is well formed. And that's definitely in Proust. This rule is definitely there. It's very important that we only form equality types for two terms of the same type. And then the only introduction rule that we have for equality is reflexivity. And that can synthesize type x equals x whenever x is a typable term. Well, more strongly, a term whose type we can synthesize. You can always write an annotation. So the fact that you need to synthesize as opposed to type checking isn't that big of an issue if you're having difficulty, just give Proust an explicit annotation, right? So for example, x can be a lambda. And then you can give it an annotation. Lambdas, you can synthesize the type of a lambda if you provide an annotation. If at the top level it's an annotation, then you can switch to checking mode, right?
Yeah.
So in order to form an equality type for a lambda, you'd actually put an annotation there for the x. Okay, so here are the easy things out of the way. What should the equality eliminator be? In other words, how do you use an equality? Any questions until now? So we've added one type. Go ahead.
I don't have a question for now, but I do have a question in the end.
Mhm.
Like when we are almost finished. I mean, I don't know what a proof of some sort of statement actually look like.
For equality specifically, or for the previous ones?
For the previous ones, or like in general, when we are working within this context.
Right.
Should it be like a program or like a function or
Well,
something?
let's actually, okay, let's, I can give you, after we do the eliminator for equality. And by the way, equality is implemented. Oh, right. So after we do equality, which is implemented in Proust, the one that you're going to start with, let's try and prove the following statement. For all B in Bool, or B with true is equal to true. Right? This is a logical statement, right?
Yes.
So let's prove that after we do equality.
Sure.
That'll actually be a logical statement where the P will not just be a thing. Depending on what B is, whether B is true or false, you get a different logical statement as a result. So that should be a good example to do.
Okay.
It was sort of hard to do the examples we considered before because it was hard to form logical statements without equality. But equality provides a source of logical statements. Like now types, if you think of types as logical statements, then equality types are logical statements. It says that two terms are equal. So would that be a good example to do you think?
Yes. Yes.
Okay. So let's get back to the question first. In order to do that example, in order to have a source of these logical statements, let's figure out what the eliminator for equality is. How does one use an equality? So given, for example, given a proof, let's say, let's use numbers for the moment, of let's say 3 equals 1 plus 2. How can I use this?
I'm thinking of like the Kong rule that we did before. Say in a logical formula that we have places where that uses 1 plus 2, then we may substitute that 1 plus 2 with 3.
Okay, exactly. Replacing equals with equals. So in other words, if I have a statement, let's say if I have, so how would you say that in logical language?
What do you mean by logical language?
Well, so before, at the beginning of the course, when I said that we had this property about replacing equals with equals, I also wrote that we won't delve into it formally for the time being, right? I said I won't give a formal definition at this point. Well, that was then. Now is now. We want a formal definition of replacing equals with equals.
Okay.
This is tricky, by the way. So let's try it.
Do we have that logical formula that we are trying to substitute with?
Sure. So let's suppose there's some logical formula. Let's call it, for example, P. And let's say that that formula has an occurrence of 3 in it. If I have, let's say, a proof of P of 3, then what?
Then we do P with 3 substituted with 1 plus 2.
Yes, we should get. What should we get?
We should get P with bracket 3 substituted with 1 plus 2.
But that is a logical statement. What are we actually producing? We're not producing the type.
We are producing P 1 plus 2. P of 1 plus 2.
But we're producing a proof of.
Proof of P
Yes.
1 plus 2.
Now, you are already familiar with what P is going to look like, right? P is going to be something that takes us something and then returns a logical statement. Now, so let's do, so this is correct. So yeah, this is exactly the right idea. Now, P should be something of type what?
Something then implies type.
Yes. And the problem, of course, is what is this something, right? What
Yeah.
do we know the something from?
Depending on what we are given, what the equal relationship is.
Yes. So if depending on what in the equal relationship?
What the type of the x where like we have x equal to x.
Yes.
Yeah.
So okay. So in other words, and then y has the same type, but let's start with x. So let's start with for all. I do want a for all. X, and let's say X has some type. Actually, but then if I write some type here, then the logical formula is ill-formed. So I should start off with for all A in type. Then I should start with some for all X in A, right? Then what do I get?
P of x for all P.
P, and what type does P have?
Have A goes, then it goes to type.
Yep. So it's a family of logical statements that are indexed by the terms of A. Then what do I need?
I need P of x.
Good. So then you take a proof of P of x. And then?
And
what
we need
type
that equal relationship. like x is equal to something.
Yes, but before that, you need the something, right?
Oh yeah, I need that something. What does x equal to?
So let's call that y.
Okay.
And then let's say for all y, what type does y have?
It has type A.
Yep. And then given this, and what do we need?
We need x is equal to y.
Yes, a proof of x equals y. And then what do we get?
We get p of y.
Yes. So this is the type of the logical eliminator. For equality. This is a formal statement of the replacing equals with equals principle. Except there's one slight modification that I make. If you give me a term x, then what can I do with x? Well, I mean, if we're forming equality types with x, then what is the assumption about x?
X is well formed.
Yes, and more strongly that I can synthesize its type, right?
Yes.
So here, the first thing in this eliminator is a for all A in type, right?
Yeah.
But we can try and synthesize the type of x. So we will try and synthesize the type of x. Of little x. In other words, I don't need to give A. Don't need to explicitly, don't need A explicitly. So this is sort of like crossing this out from the quantifier. But it's still important when forming this, or otherwise A would be a free variable, but we still keep it there. So otherwise, if we synthesize the type of this synthesize A, then how many arguments do we have in the eliminator otherwise?
4?
Nope.
5?
5. So the x, the p, the proof of x, the y, and the proof of x equals y. 5 arguments. So going back here to our grammar, equality, the eliminator for equality is going to take 5 parameters. And let's give a typing rule for it. So let's say we have an EQ elim. And then what should I call the arguments?
X, P,
Mm-hmm.
Proof of X, PX,
Mm-hmm.
and Y.
Let's
Else?
call it PEQ, proof of equality.
Okay.
So this should synthesize to type what?
P of Y.
Exactly. And then let's write what I needs to do in order to conclude this. What's the first thing that I do?
Synthesize X.
Yes. And I guess that handles both of the first two things here, right? We assume that anything that gets synthesized is a type. So if synthesis succeeds, then A is a type. That's going to be an invariant in Proust. Next.
Then we check whether P has the form that P is A implies type.
Yes. Then
we check whether Px is P of X.
Good.
Y type checks to A.
Yep.
And PEQ
Mhm.
type checks to X equal to Y.
Exactly. So we can read it off from here. So that rule, it was hard to figure out what it was initially, but you actually got it right away. I'm impressed. That was quick. So there were several properties of equality that we stated. Symmetry, reflexivity, but then there's the replacing equals with equals. And it turns out that things like transitivity and symmetry are consequences of this. You can prove transitivity of equality and symmetry of equality just using this replacing equals with equals property. This is how you actually use an equality. So I'm not going to give you the strong reduction principle, but also this is going to be a very high level abstract statement, which is somewhat mind blowing. So if we looked at, for example, Booleans, Booleans were an inductive data type. A Boolean is either true or false, right? And then if we looked at, one second, what am I going to say? Right, if we looked at the type of the Boolean eliminator, the question was, how do I prove something for all Booleans? Well, I say what it is that I'm trying to prove. I give the property, and then I give a proof of true and a proof of false, right? And once I've done those three things, I've proven it for all Booleans. Does that make sense?
Yes.
Now let's think about it for natural numbers. How do I prove something for all natural numbers apart from the anonymous method? The induction principle for natural numbers is that you give me the property, you give me a proof of Z, you give me a proof of the successor case, and then the conclusion is that I've proven a statement for all natural numbers, right?
Yes.
Now let's look at the induction principle, which we've called now the elimination principle for equality. And notice that I've separated it onto a separate line. You give me X, you give me the property, you give me P of X, and then what's the conclusion? I'll write it in a different color. The conclusion is that for all terms Y of type A, for which X equals Y, P of Y. So in other words, what I've done is I've proven that the property holds for all Y that are equal to X. Now, depending on what the eliminator is, which I'm not going to give you today, you might think of the eliminator as being you look at the proof of X equals Y and you use structural induction on the proof to construct a specialized proof term for P of Y. So that was an incredibly high-level abstract statement. What do you think of that?
Is mind-blowing.
And then it's the structure of the eliminator suggests that that's true. And so perhaps equality is also an inductive data type, although it's not currently in proofs. Currently, the eliminator is the strong reduction principle is very bad. Currently, the strong reduction principle returns the proof of X for the proof of Y. And I can show you a case where that breaks. But so that might get fixed soon. But for the moment, it just returns the proof of X in place of the proof of Y. If X equals Y, then it should work, except not exactly. But we're not going to change the grammar. The grammar is this. This is the induction principle. This is how you prove things about equality. You have equality elimination. Now, but I can tell you one thing. I can tell you computationally, what is the meaning of an equality? Well, if two terms are, computation should take equals to equals. So I will tell you a bit about the eliminator for equality. How much is a bit? So for example, if you look at the proof of, let's try and prove the following statements. Plus Z equals Z. So what happens is that this is actually not the strong reduction principle for equality, for the eliminator for equality. It's the strong reduction principle for equality types themselves. So here, for example, we could form the type well, right. So here, I'm going to switch to proofs now. So Proust also has equality, and this is in the version that you're starting with. And it has reflexivity, and it has the eliminator for equality, 5 terms. Now, if we look at strong reduction for actual equality types, the type of equality is TEQ. You see that what happens is that the type of equality A equals B, its strong reduction is the type of equality of the strong reduction of A and the strong reduction of B. And the idea is that anything that strongly reduces to another thing is equal to it. And this is also true for types. In other words, we can consider, for example, parse expression. And then we can consider the expression true equals true. So that's the type of equality of the term true with the term true. And then if we, for example, try and synthesize this type in the empty context, what do we get?
TEQ.
We're synthesizing the type of it. So we're trying to synthesize the type of TEQ true true.
That's a type?
Yeah. Now, so then we can consider, okay, well, what happens if I write true and then Z?
That's nothing. That's
yeah,
a
cannot infer type Z. It'll try and type check Z against it. That will fail. It'll try and do a turn rule maybe, but yes, that fails for one reason or another. Now, what happens if I consider something like, well, Oh, right. I don't have natural numbers right now. And it fails because I don't have natural numbers. Let's try true equals type. True is a Boolean, type is a type. Then it'll actually say cannot type check type as Bool, right? It synthesizes the type of true to Bool, and then it tries to type check type against Bool, and that fails. Now, let's consider, for example, true, and then let's consider another thing here. We have and or defined, right? So we can say and true, true. And then that should work, right? And true, true is a Boolean, right?
Yeah.
So that works. Now, what happens if I strong reduce this?
Should be true equals true.
Yes. So in other words, if I look at this expression right here, that was a type, and that type was the type of equality with true with the application of, well, and applied to true and then true, right? And the fact that these two were related with this equivalence relation, the three lines, means that, for example, if you try and type check a term against this, or if you use the term rule and you're able to synthesize a type, then it'll compare types for equality. And these two types will be definitionally equivalent. So in other words, what is a proof of true equals true and true? How do I prove this? Remember, this type is the same as this type. How do I prove this? Let's try this first. How do I prove this?
By applying what's that function called? Reflexivity?
Reflexivity of equality.
Equal true.
Let's check this. So by the way, this version of Proust has a function check1, which will parse this expression, and then it'll try and synthesize its type. And will it give me an output? Okay, it'll give me the output of the synthesized type. So it took this application and it synthesized the type 2 true equals true from it, right? Now, what about if I'm not trying to prove this, but I'm trying to prove and true, true? Will that proof work?
No.
Why not?
Because instead of true in the second after the equal sign, we have a and type that is I mean,
right.
It should
So but let's look at this. Let's say we try and type synthesize. Actually, let's just write check1. And let's not even provide an annotation. Let's just provide a term, EQ reflexivity true. So this will attempt to synthesize the type of it. What type do I synthesize?
Is a tag true equals true.
Right.
That will be a type.
Well,
Um,
of the term EQ refl true, its type is true equals true, right?
Yes. Yes.
So now consider this. how will it type check? How does one synthesize the type of a of an annotation? Well, so it'll try and type check this against this, right?
Yes.
But there's no rule for type checking EQ REFL. There's only a synthesis rule, right?
Yeah.
So in other words, it'll apply the turn rule and it'll synthesize this type, right?
Yes.
And then it'll compare the resulting type, true equals true, against this type, right?
Yeah.
And it'll compare them for equality
yeah, and they're
after
not
reducing them.
after reducing them.
The
So
3 lines, the definitional equality, the 3 lines also include computation in them.
so that should return true equals true.
Yes, and it'll compare those two, and it'll be equal, so the synthesis will succeed. And then this line will return the synthesized type, which is true equals true.
Huh.
Actually, it won't return true equals true because it'll return the type of the annotation. So it'll actually return this.
That's very interesting.
And if instead, if I put true equals true here, so the computation happens only when verifying the turn rule, right? But after the turn rule, what's returned isn't the reduced version of it, it's the original version is returned. Specifically at the top level, this is an annotation. And if we look at the type synthesis rule for an annotation, what happens is we type check T against type, which it is. Then we type check E against T, and then we return T. So no matter what, when we try and synthesize the type of an annotation, if it succeeds, it'll return exactly what was on the right-hand side of the annotation. So all of these rules exist, but I'm just telling you on authority what some of the consequences of the rules are. But that's why it behaves like this. So you don't have to understand every single detail of what's going on, but do you just see the general picture?
I see. And a proof that we are looking for should resemble, should have the form of annotation.
Oh, so on the reason that you that will change it into checking mode. But notice that if you have, for example, check 1 equals reflexivity true, the reason that that succeeds is because that synthesis mode succeeds for that. Whereas this, well, I guess synthesis mode would succeed as well, but this will return that. In general, you could write things like check 1. So let's do the polymorphic identity function. Did we have that at the start? Oh, let's actually make a definition. Let's see, have I already defined them at the bottom? Well, okay. So let's define ID. Have we done this here? No, we haven't. Okay, what's the definition of the polymorphic identity? Oh, sorry, ID type, let's say. What's the type of the polymorphic identity function?
For all X
Let's say
in type, A in type, A implies A.
And then let's actually give it a term. So let's give it ID, and let's give it a term of that type.
Lambda A. Then lambda B.
Well, it's something of type A, right? Little a. A.
Lambda A, okay. Then lambda X. It can be
What is X?
X is just A, right?
Well, so this lambda corresponds to this for all, right?
For all.
And then
yeah.
this one corresponds to this one. Then we just want to return
A.
something of type A.
Yeah. So we just need 2 lambdas.
Yeah. Which we have.
And then we just need A.
Yeah.
Which is the little a.
So this should be something of ID type, right? But
Yeah.
if we just try and synthesize the type of this, then that'll fail, right? Because how do we synthesize this type? So this will fail, right?
Yeah.
Cannot infer the type of this in this context. But on the other hand, if we take that and we provide an annotation saying that the type that I intend for this to have is ID type, then that should succeed, right?
Yeah.
And then I can, for example, write strong reduce. And strong reduce will, for example, expand definitions in the empty context. And that'll give me the term, right? Right, well, this was a bit off topic, so these are some definitions. Right, wait, where was I? Okay, I wanted to prove the result that I said we'd prove. So what was the results? Let's call this theorem. So what did we want to prove? Do you remember about Booleans?
Yeah, it's for all bool B, or true B is equal to true.
Yes. So we wanted an equality type. So that's a well-formed type, right?
Yeah.
So that succeeds. Then we can, for example, ask things like type synth of theorem, empty context. What do I get?
We get a type.
Yep. Not a type. Type.
We get type. So it's the type of theorem.
Yes,
that
it is.
type.
Yes. This thing is a type itself, and so its type is type.
Okay.
Now, what if I instead strong reduce? What do I get?
We should get the definition of theorem.
Exactly. Okay, now let's try and prove it. Let's do check 1, and then let's write the proof term. And then colon theorem. So what's the proof term?
We need a lambda.
Good. So, whoops, command. And then let's say takes B.
Okay. Then we should probably use the limiter of equality.
Yes. So EQ ilim. Now, do you remember what the order is? It would be impressive if you did. Although they're also in somewhat logical order, so it is possible to figure it out.
Yeah, it's difficult. Let's see. I mean, I want to state it in the right order.
Wait a second, but before we say that, before we do that, in order to eliminate an equality, we need an equality to eliminate, right? We don't
Could
have an
you-
equality. We have a Boolean.
We have a Boolean.
How do we use a Boolean?
Okay, that's a Boolean elimination.
So it's not an equality that we're using. It's a Boolean, exactly.
So B is for all B in Bool. And our goal will be proving A or true B equals true.
Exactly. So the lambda should be what?
Lambda should be
I'll switch to this mode. The property.
yeah. The property. Still X dot Bool.
Oh, but what are we trying to conclude? You said it before. It's not we're not trying to produce a Boolean. We're trying to produce
An equality type.
yes.
Let's
So of what?
of or true B equals true.
Yep. Or but B doesn't make sense at the moment. Actually, well, we don't want B. We want to make reference to what do we put here?
We replace it with equality elimination.
Or so we're trying to prove something for all Booleans, right? What are we trying to prove for the Boolean X?
It's a specific Boolean. We cannot use B because B has been defined to be for all B in Bool.
B is going to be what we're going to put in the last position of the eliminator.
I see. So what's that gonna be? No.
Well, this is the property that's indexed by Booleans, right? This is P of X. You're defining P in terms of X.
Oh, so that'd be or true X?
Yes. So we're trying to prove this for all Booleans. So this is how you go from a Boolean X to the result that we're trying to prove. Before, we did not have X participating. Before, we were just doing recursion to define Booleans. Now we're actually using induction to prove theorems. And here the theorem actually depends on the number that Boolean that we're putting. So here's our first actual theorem that we're proving by induction, although the induction is on Booleans. The induction principle for Booleans is less elaborate than the one for natural numbers. Okay, so that's the property. Now what do I need?
I need the proof when B is true and the proof of B is false.
Exactly. And what are those proofs?
That will be or true is equal to true. I mean,
but how do I prove that? I need a proof, not the proposition.
Well, if I know what a proof looks like, I don't have to ask this question, but I mean, so is to write a proof, we have to know what a proof looks like.
Well, so let's see. The thing that we're trying to put here is going to, it should be something of type what? It should be a proof of P true, right? What is P true?
P true is or true is equal to true.
And how do I prove that?
I strong reduce it.
But strong reduction isn't a proof term. What's the only proof term that we have that proves equalities?
That prove equality reflexivity.
Right, and we'll just, so I want to put an EQ reference. And what am I going to claim is a proof of this?
True.
So that synthesizes a proof of true equals true. Is true equals true the same as this type?
Not really. Yes, yes.
It is.
They should be of the
But
same
strong
type.
reduction, the true equals true is the same as this.
Hmm.
So the proof in the true case is just EQ ref true. Now what about the false case? What are we trying to prove there?
Or true false is equal to true.
And what's the proof of that?
EQ ref true.
Yep.
Oh, that's it.
So
And
those you
apply it
for
on B.
true and proven it for false. Now what do we do?
And we apply it on B.
Yep. So that closes the Bool induction principle. And now you have lambda B.
Hmm.
So given any Boolean, this produces that proof term.
Wow.
And now we are claiming that this is a proof of what theorem, right?
Yeah.
So let's check this. Bam. We've proven it.
Huh.
So what you were given is a Boolean. And how do you use a Boolean? You use a Boolean by using the induction principle on it. What is going to be the results type of what you produce? Well, that depends on what Boolean you're given. So you write an index for the theorems, indexed over Booleans. Then you provide a proof in each case of the grammar, and then you give it a Boolean.
I see.
How does this all work? It's the rules. If you look through the rules, it is very difficult to come up with those rules. But if you very carefully think for a very long time, you can come up with these rules, and then you can get logic on a computer. This is logic on a computer. We can do math here.
Yeah.
So on Monday, I'm going to have another full lecture, and I'm going to do a lot of the same things that we did, but I'm actually going to put up the programming and proof assignments. The programming assignment is going to be to implement natural numbers. And you, I know for a fact, see that it's very similar to how we implemented Booleans, right?
Yes.
And then there's going to be a proof assignment where we're going to prove plus Z. And you're going to implement natural numbers and you're going to prove theorems about it. But here's a really good exercise. So I'm happy we did this one about how to prove properties about Booleans. This is a proof of a for all Bool statement. And the thing that we proved is an equality. So all of it comes together here. Now, in order to talk about this, we didn't have to talk about the strong reduction for eliminators for equality. There are no equality eliminators in this proof. There are only equality introductions. There's a Boolean eliminator, and we know what the Boolean eliminator is, what its computation rules are.
Yes. A quick question.
Yep.
So can I do the proof similarly like what I did for the previous assignments, where I can do the these proofs step by step?
That's the problem. In the presence of dependent types, it is much more difficult to implement holes.
So
the
that means
replacement for holes is definitions. We introduce definitions in order to compensate. You can build them piece by piece, but you can't. The problem is that the pieces have to make sense, in which the only free variables inside of them can be other global definitions. But you can't have a whole where you have some things in your context which aren't proven yet.
So we have to come up with these proofs just in one step, like that.
For this one, yes, you'd have to come up with it in one step.
What do you mean by this one? Like there are other ones?
No. You see, if you're trying to prove a proposition, you probably have to do it, but you can think of a lemma coming up, and then you can prove the lemma.
I see. Similarly, like what we did for what we did at the beginning of the course.
Yes. So for example, you can prove there's, oh, by the way, before we can prove some of these results, there are also going to be some theorems about equality. So for example, if you saw the computation, we did weak compute blocks, right? And in weak compute blocks, we stringed together several equalities.
Yeah.
Now, in order to string together several equalities, you need to prove transitivity of equality. And that's not something that we have yet, right? If A equals B and B equals C, then A equals C. That need requires proving. The only way we have to use equalities is the equality eliminator. So you're going to have to prove transitivity of equality first and symmetry of equality. And then using those, although symmetry probably won't get used, you can prove plus Z.
I see. Plus Z.
But you're going to have a lot of lemmas like transitivity of equality. Before, we didn't use transitivity in a formal way. We just said we're going to not require you to explicitly write what properties of equality are. But here, equality is purely formal, and anything that you want to use about equality, you have to prove about equality. Well, you're going to see the assignments, so I trust that you're going to be able to do it.
Oh. Okay. It's gonna take a lot of time, I suppose.
It's going to be very tedious because, yeah, that's a good reminder for people watching. Everyone needs to hear this. Remember how we have a very large number of functions now. Let's see, there's parsing, there's pretty printing, there's substitution, there's free in, there's alpha equivalence, then there's strong reduction, and all of these have every single grammar construct appearing in them. So when you add, for example, natural numbers, there are 4 new grammar constructs, right? The type, nat, Z, successor, and the induction principle, right?
Yeah.
So you have to add 4 cases to each of these functions. And then there's type checking and type synthesis. Well, most of them will be added to type synthesis, right? So you need 4 new cases in type synthesis, and then 4 cases in all of the other functions that I mentioned. But if, for example, if you look at, for example, how substitution works, if you have really any structure, it just substitutes inside any of the substructure. Substitution is only tricky when you have arrows or lambdas. Here, you just add them in without thinking. You just recursively substitute inside, like the rule we had for applications. Similarly for pretty printing and parsing. The only really clever ones would be you need to have the correct strong reduction principle for the eliminator for natural numbers. And here you have the rule for eliminator for Booleans, so you try and mirror this. And then, okay, I guess for type synthesis, it's fairly straightforward because you just need to check all of the things. I have them written on, I had them written on the board before, right?
Yeah.
But it does take a very long time to get used to how these proofs work. But you only have to do it once. So after you get used to writing proofs, you will now know how to do math on a computer. So it's worth it. Okay, oh wow, we went quite a bit over. But any other questions? It's sad that no one else is here, but we're going to have lecture on Monday.
Oh yeah. So when can we expect grades for the midterm?
Oh, Marmoset was down yesterday. It's up now. I'm going to do those tonight.
Okay.
I've been behind on that. I'm going to make a point of doing it tonight. I'll send everyone individual emails with reports of their grades.
Another question.
Mhm.
When will the next assignment be due?
Because of the power outage, I'm going to put a fairly late deadline on it. But we have a final exam, which I also need to figure out what day. And I want to have it due before the final. But I think the assignment should be due at least on Monday or Tuesday, probably Tuesday.
Monday or Tuesday. How many more assignments do we still have left?
Well, this is the end, really. So I think there might be there's a proof assignment with just for alls and equality that you can do without the programming assignment. Then there's a programming assignment. Then there's another proof assignment. And depending on what decision I make, I might also have another programming and proof assignment for existential types. So for exists as opposed to for alls. But that would be very late game content, and it almost looks like we don't have time for that. So really guaranteed 2 more proof and 1 programming assignment. And
Okay.
those are really in service of being able to prove plus Z. So the first one is basically properties of equality. Then programming assignments to get nats in, and then proving some properties about nats.
Okay. Okay.
Oh, by the way, let me make one more remark. If you look at this, the proof that we had right here, well, this lambda produces a type, right?
Yeah.
What if we just, instead of putting or true x, puts true equals true? Would that work? Let's see. I actually don't know if it would. Because, no, it wouldn't. It wouldn't. For a fact, it wouldn't. Good. Yeah, so you can't do the strong reduction at this point because you don't know what x is. But here you do manually do the reduction when x is true and then when x is false. But you can't do the reduction when x is indeterminates. As for y, look at the rules. The rules will say. A lot of figuring out how this works is looking at the rules and figuring out what happens. Because after all, Proust just directly implements the rules. It doesn't think, it just follows rules. And it's possible to figure out what the results are just by following the rules, right?
Yeah,
Now,
it's
how
like
to actually write the proofs, you need to be clever.
I see. So it's not like computer understand this math. It's like we understand the math and we tell the computer what the rules are explicitly, and the computer just dumbly follows these rules.
Yes. And you also tell the computer what the proof is onto which to apply the rules. So if you think about, for example, the Boolean interpretation, you can determine whether a theorem is true or false by checking exponentially many options in the Boolean interpretation. Here, the proof term is not exponentially large. Well, I guess there are only so many things appearing in it. But also, I haven't given you like what the Boolean interpretation is for predicate logic. That's different. That actually is model theory. That involves checking all possible interpretations of things, of which now range over uncountable structures. Well, okay, not necessarily that, but it's much harder to write an algorithm to determine the validity of statements with quantifiers in them. In fact, it's impossible. In fact, the classical problem that's uncomputable is determining whether a formula in predicate logic is true and false. There's no algorithm that lets you determine that, as there was for the Boolean interpretation. In fact, Church's original proof of an uncomputable problem was the proof that using lambda calculus. He introduced lambda calculus to prove that the problem of solving a system of polynomial equations was undecidable, that there could not be an algorithm that did that. And that is equivalent to saying that's the problem of checking whether a formula in predicate logic is true or false. There's no algorithm for that. It's impossible to write such an algorithm. But you can write proofs cleverly. You can find proofs for true theorems, and you can have a computer check them. But that requires cleverness on your part. So it's impossible to do it without some cleverness. There is no algorithm to find proofs, provably. Okay, I think that's all for today. Any other questions?
A quick one. When will we have our final?
Okay, I need to decide based on the power out. I'm traveling back to the US on Tuesday, and I'd like to do that after I travel. So probably Wednesday to Friday.
Wednesday to Friday. Next Wednesday to Friday.
Yes.
I see. Next Wednesday to Friday. That means we are going to have a class on Thursday?
No, I think probably Monday will be the last lecture.
So are we going?
Today was going to be the last lecture, but that's obviously untenable given that the storm prevented everyone from attending.
So when will we talk about existential quantification?
On Monday.
Okay.
It's actually it's much easier than talking about equality.
I see.
It's actually it's easier than even talking about universal quantification. So existential is actually a very quick assignment relative to the other ones. But I'm not sure if we'll have time for it. So that's another thing. I'm going to have to determine that over the weekend.
Sure.
Anything else?
No.
Okay. See you on Monday. And I'll send out the assignment tonight. And also midterm grades. Although that might be later tonight, like much later. Okay. So hopefully this lecture was enjoyable. See you on Monday. Bye.
Bye.
Bye.